So today what we'll do, we'll start with this new thing, the continuous time Fourier transform. Okay, or it is simply called as the Fourier transform. Okay, because this is the first thing Fourier transform that exists within the textbook. They call it that way. So while studying the discrete time Fourier transform, we related it with the Z transform, right? So whenever you study the continuous time Fourier transform, we'll relate it with the Laplace transform. Okay. So what is the similarity? You have to replace, if at all you replace your S by j omega, if at all you replace your S by j omega, then your Laplace transform translates into the Fourier transform. Now, what is the difference, by the way? Actually, your Laplace transform had S plus j omega. Remember, S equal to sigma plus j omega. There is something related to real part, imaginary part, then there is a damping indicator, right? Something that there was a sigma. But here, when we are talking about Fourier transform, we will assume that Fourier transform is always stable. Okay, so there is no question of a sigma coming in the Laplace. That is why we will simply have to represent S by j omega without considering the sigma part of it. Okay, so let us get started. So what is the formula? The formula for here it is. So this is the formula for the Laplace transform. As I said, the continuous time Fourier transform exists for continuous time periodic signals. We know this, right? Fourier series exists for periodic signal. The Fourier transform exists for periodic signal. There are exceptions. Okay, there are exceptions. We'll study later. Just like we had the Fourier transform for the cos wave also, right? In the previous topic. Okay. So the formula, you can see this formula looks very similar to your Laplace transform, right? The formula looks very similar to your Laplace transform with a small change here, right? So with a very small change here. So this is the formula, x of omega equal to minus infinity to integration over the entire signal x of t e to the power minus j omega t. And how do we get the original signal back? It's by 1 by 2 pi minus infinity to infinity x of omega e to the power j omega t d omega. Okay, this is the formula to get the original signal back. Okay, so 1 by 2 pi minus 1 infinity to infinity x of omega e to the power j omega t. So you can see the change in the signs here. There is minus sign here, whereas in the inverse there is no minus sign. Okay, so this is how we represent it as the Fourier transform pair. This is how we represent it as a Fourier transform pair. Okay, so shall we? Anything peculiar here? Yes, earlier in DTFT x of n it was continuous. So what are we actually trying to do? What we are actually trying to do is we are trying to represent. We are trying to. Okay, yes. Clear. Okay. So what we are trying to do here is, let us see this in the form of this expression only. Let us see this in the form of this. What we are trying to do is, we are familiar with x of t being represented as a wave, something like this, where you have x of t being represented as a variation of time, right? This is we are familiar. Here you can see for a change, they are representing x of t in terms of the coefficients x of j omega, where this omega you can see keeps varying, right? So you can see this is like your DTFT only. Instead of summation, here you have integration. So here we will have in terms of several omega. So what you are doing is, you are trying to represent this particular wave as superposition of complex sinusoids, as a superposition of complex sinusoids. Okay, that's what you are doing. Where this x of j omega, the Fourier transform coefficient, lets you know exactly what is the contribution of each frequency. Okay, got it? Isn't it interesting? Okay, that's where x of j omega gives you the very information. What is the contribution for individual frequencies? Okay. So does x of x of omega, by the way, the Fourier transform exist for all the values? So I, as a student, I always got confused. Which is the Fourier transform? The first one or the second one? This is the Fourier transform. Okay. This here is a way to express x of t in terms of Fourier transform. This actually is the formula for the inverse Fourier transform. Okay, do not get confused. Hmm. So the Fourier transform doesn't exist for all the values. Okay, so the condition is your x of t should be integrable. Okay, x of t should be, if at all I have x of t as 2 to the power t into, okay, if at all I have my x of t as 2 to the power t. So does this expression here, does it have a Fourier transform? Does it have a Fourier transform? 2 to the power means 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So this is going to be a growing exponential on the right side, decaying on the left side. So since this here doesn't seem to satisfy this property, this is not converging. So for this signal, we do not have the Fourier transform. What about 0.5 to the power t? What about x of t equal to 0.5 to the power t? Does this thing have a Fourier transform? Okay, what about x of t equal to 0.5 to the power t? Does this thing have a Fourier transform 0.5 to the power t? No, I guess, right? So because 0.5 to the power t, 0.0 to the power 0, 0.5 to the power 1, 0.5 to the power 2, and so on. It's a decaying exponential on the right side, but it's a growing exponential on the left side. Okay, so this also does not have the Fourier transform. So which kind of signals have Fourier transform? Signals which is something like x of t equal to, now let me write this particular signal. X of t equal to what? 0.5 to the power t, 0.5, 0.5 to the power t into u of t. So when I multiply this with u of t, now this signal exists only on the right side. Okay. Now this signal you can see is a decaying exponential on the right side and it exists only on the right side. So this is converging. Okay. This signal converges, and for this particular signal we have a Fourier transform, or 2 to the power t, 2 to the power t into u of minus t, 2 to the power t into u of minus t. This signal also, because this is growing on the right side, but it is decaying on the left side, going on the right side, but who is taking right side? See, u of minus t. So this is decaying on the left side. So this also will have the Fourier transform. Okay. So what is the condition for the Fourier transform to exist? X of t should be integrable. Okay. And it should have some finite local maxima and minima. Okay, let's not bother about this. And then the size of these two expressions, let us not bother about these two expressions for the timing. Let us stick to this. Okay. Let us stick to this one. Okay. So only for certain conditions, these two expressions. By the way, they are called as Dirichlet conditions exchange. Okay, very difficult to pronounce also. Anyway, so let us now move ahead. So what is the formula? Here is the formula for Fourier transform: x of t e to the power minus j omega t. But whenever you substitute, you should check the range for which this is converging. Okay, wherever it is diverging, the Fourier does not exist at all. Okay, now let us see what are we trying to do here. So whenever we are trying to learn some new topics, basically it's good to know eventually what we are trying to do, right? Eventually what we are trying to do. Here, let us say, I will just give you an example. Say there is a circuit in the laboratory. Say there is a circuit in the laboratory, a continuous circuit. Same is the case we saw earlier, right? The last problem in the DTFT, there was a circuit, one with the feedback path, one with the feed forward path, and we could predict how does the circuit behave for different frequencies. So here also something said, I have this particular RC circuit. I want to know, you can see this is R and a C in parallel, right? This is going to be, sorry, we do not know what this is going to do, right? There can be so many circuits like this. So what you have to do is, you have to somehow relate the input and the output via a differential equation. You might have solved this kind of problems in your mathematics or in your network theory, right? So what you have to do is, you have to just have to represent them in terms of a differential equation. Then afterwards, my worry is, I want to know this particular, so how does it behave? How does it behave in the frequency domain? Maybe I want to implement a low pass filter or high pass filter. I want to have a filter which will allow everything up to 500 hertz and suppress everything above 500 hertz. Or I want a circuit which will select only the frequencies from 1000 hertz to 1500 hertz and reject all frequencies in all other places. Okay, that is my situation. So if at all I want to do that, I can analyze that by going for, you know, describing the circuit in terms of a differential equation, then take the Fourier transform, right? So now this is a Fourier transform. What did I do? Y of t and x of t are my input and output voltages. Let me apply the transform. Let me apply the transform and take the ratio. Now this taking the ratio of output response by input response gives you something called as the frequency response. Now this here, omega naught here is 1 by RC. If at all I split this in terms of magnitude and the phase angle, I am getting a frequency response. Now, what information does this give? So, are you getting this thing here? You can see now this circuit here is telling me that as and when the frequency increases, the gain of this particular circuit goes on reducing. That means this here can work as a low pass filter whose cutoff frequency is 1 by RC. Any frequency above 1 by RC will be getting a gain less than what is this, 3 dB, right? Log of 1 by root 2 is minus 3 dB. Before that it again more than minus 3 dB to 1. Okay, are you getting this? By the way, what are we trying to come to eventually? So we want to know for every given circuit, we want to know the frequency behavior. Or on the other extreme, what we can do, say I want a frequency response where specifically, right, I want to see a star sports channel which is there from 44 megahertz to say 49 megahertz. Okay, specifically, then what I can do? Say from a circuit, I can arrive at the frequency response. Then don't you agree that from the frequency response, I can get the circuit also? Yes, why not? Okay, it is also a possibility. So this is what we are trying to do here. So Laplace and your Z transform were more about stability, right? But here in the frequency response, what we are trying to do, we are trying to tune things. We are trying to get circuits which will give a behave in the frequency domain as per our requirements. We want to do the analysis of the circuits, how do they behave, or we want to synthesize the circuits the way we want. Okay, so let us get started. Let's get started. Okay. So here we are. So let us start with some very basic signals. Okay. Why are we interested in basic signals? We want to, later while we are want to, by using the ready results from the basic signals and the system properties, we want to find the Fourier transforms of much more complicated signals. Okay. That is the whole idea. Okay. Let us see what is the standard signal. Yeah, this is one of the usual suspects. Okay. It's a real exponential. Okay, it's a real exponential. I hope most of you remember what was the Laplace transform of this particular thing, right? It is 1 divided by a plus s, if I'm not wrong, right? Is it? I'm not so good in the Laplace thing. Anyway, so, so here is the Fourier transform. So what is the behavior of this particular signal? E to the power minus at into u of t. How does the signal behave? You can see there is a minus sign with a. Okay, so that means if a is positive, something like 0 0.2, 1, 2, 3, then we will get e to the power minus 0.2, e to the power 1. So this will be, I will write this thing as 1 by e to the power 80. Okay, this is a more convenient representation. And whenever this a is a positive quantity, the denominator goes on increasing exponentially, and the entire term goes on decaying exponentially only on the right side, because I have a u of t multiplied here, right? It's just only on the right side. But what will happen if my magnitude a is less than 0? If my magnitude a is less than 0, say minus 0.5 or minus 1, then what's going to happen? I will get a minus sign here. So 1 divided by a decaying exponential, right? Because you get a minus sign here. 1 divided by decaying exponential will give you a non-converging growing exponential on the right side. So for this particular thing, the Fourier does not exist. Okay, that is why author first starts by the statement that Fourier transform does not converge for a less than 0. Okay. So this is the first statement by the author. So this is going to be infinity, does not converge, does not exist at all. So this is the first statement. For a greater than 0, now we are talking for a greater than 0. Now let us do the integration. How is this happening? E to the power minus 80 into u of t. This u of t will be absorbed by us writing the integration from 0 to infinity. Exists only on the right side. And we have this particular thing, something like this. How did this happen? How does this happen? Here, okay. So what is the expression? E to the power 80, right? E to the power minus a. So integration of e to the power j theta is e to the power j theta divided by minus j. Let us have the minus sign here, and j omega. Integration from 0 to infinity, right? Not from minus infinity to infinity, since it's existing only on the right side, from 0 to infinity only. So what do we have here? 1 divided by a plus j omega, which is part of this expression, the constant. And here, e to the power minus infinity minus e to the power minus 0. E to the power 0, this is 1. So we have minus 1. This term here is indicating 1 divided by e to the power infinity. 1 by e to the power infinity is 1 by infinity. 1 by infinity is how much? 1 by infinity is 0. So this term is straight away 0. This term is 1. 1 into minus 1 into minus 1 is equal to a plus 1. So we have this answer 1 divided by a plus j omega. Okay. 1 divided by a plus j omega was the answer. So this is, I think, yes, yes. Anything? Anything? What happened? So, 1 divided by, what is it? Hmm? Okay. So, 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 yeah. So, I wanted you to understand that this was very similar to your Laplace transform, very similar to your Laplace transform. S replaced by j omega. Yes, we remember this. 1 divided by a plus s. We remember this, right? Now, this is not sufficient for us to. We want to know how does the shape of this look like? How does the frequency response look like? So, what we will do is now let us get the magnitude and phase response of this. Okay, let us get the magnitude and phase response. Here, author has done it. Here, author has done it. Got the magnitude and phase response. So what is the magnitude of this one? 1 divided by square root of real part plus square root of real part square plus imaginary part square. Yeah, there you have it. This particular thing is the magnitude. What is there to understand here, by the way? You can see this is the variable, right? Omega. This is a constant. You can see this omega, as and when omega increases, as in there is a square term here. Okay, as and when omega increases exponentially, the entire term has to decrease, right? So what we will do is usually we will indicate the value at 0. Okay, simply substitute omega equal to 0. Okay, so 1 divided by a root. Okay, so at 0 we usually indicate the value, and at these 2 points. Remember these values. Remember these values if possible, because this is a standard signal. Okay, and phase angle. You can see minus tan inverse of imaginary part by real part. Okay, so you got this particular phase thing here. Did you observe one thing here, that the discrete time Fourier transform was existing from minus pi to pi? Discrete time Fourier transform existed from minus pi to pi, whereas this continuous time Fourier transform, this one here, it existing from it's existing from minus infinity to infinity. Okay, okay, it is existing from minus infinity to infinity, but what we are doing is, still you see the formula for the inverse. The formula for the inverse here still has a 1 by 2 pi in it, right? So this 1 by 2 pi we used in DTFT, because DTFT was periodic from minus pi to pi. But here they are retaining this 1 by 2 pi term, whereas the entire thing is going from minus infinity to infinity. Okay. Remember, the DTFT was continuous and periodic, whereas the continuous time Fourier transform is continuous, but it is aperiodic, goes from minus infinity to infinity. But this 1 by 2 pi still there. Okay, 1 by 2 pi will still be there. Okay. Okay, okay. Now let us yeah, see. So a real exponential existed only for a greater than 0. This was the first thing. Answer very similar to your Laplace transform. but we wanted to know the frequency response. That's why I took the magnitude and phase, and it turned out to be an exponential, turned out to be something like this. Okay, exponential turned out to be something like a bell shaped curve. Okay, and with the frequency response, something like this. One more thing that we saw was the DTFT was aperiodic in nature from minus infinity to plus infinity. Okay, now let us continue. Let us continue. What next? What is the next standard signal? Yes, it is the rectangular pulse. Okay. So here it is rectangular pulse. So can you guess what is the answer of the rectangular pulse? Usually, whether it is continuous or discrete, the DTFT of a rectangular, the Fourier of a rectangular is sinc. The Fourier of sinc is a rectangle. Okay. So here is a standard signal once again with some minus t and plus t. If it is minus 4, then you have to substitute a 4 here, minus 4 to plus 4. So remember, all these values they indicate it's like a formula. All these numericals are like formula which we may use at a ready result as and when situation arises. Okay. Okay. So here we have. So today also I'm telling the moment the time ends here, I still have 5 minutes to go. The moment the time ends here, I will send you the ID password. Please join me for another 5 to 10 minutes. Okay. Usually most of them simply leave and oh, फिर नहीं आते. I don't want that situation here. Okay. Okay. So yeah. So what do we have here? Hmm. So x of t is equal to, yeah, a normal rectangular pulse. So now we do the integration from minus t to plus t only. We substitute, and what do we get here and why do we get here? Here I have the numerical. So what do we do? Yeah. So what do we do? Yeah, e to the power j omega t minus t to plus t. We have minus t to plus t here. So this particular thing compels us to use. We already know it's a rectangular pulse. We want the answer to be sinc pulse. So sine term has to be there. That is why first thing what we'll do is we'll get this it in the form e to the power j theta minus e to the power minus j theta divided by 2j. 2 is missing. So we will put it here as a part of compensation, and we have sine omega t. Okay, what is e to the power j minus e divided by 2j? 2 is made for this, j anyway get cancelled because we represent. Now there is a catch here. Now there is a catch here. You can see this expression sine for omega equal to 0. For omega equal to 0, sine 0 is 0. 0 divided by 0, it is going to give infinity divided 0 divided by 0 for. It's going to give 0 divided by 0 for. So that for omega equal to 0 case, what we'll do is we will try to substitute it here. Okay, here we'll substitute for omega equal to 0. What will get omega equal to e to the power 0? E to the power 0 is 1. So what do we have here? T plus t, 2t. So for this particular case, omega equal to 0, we will get 2t by substituting it here. Or otherwise, author says that for very, very small omegas, for very, very small value of theta, author says sine theta is theta only, it seems. For very small values of theta, sine theta is theta only, he says. Okay, for minute value. So that means it is very fair to assume sine omega t is same as omega t for small value, right? Omega equal to 0 is a very small value only. So then here also you can still get omega for omega equal to 0 2t. Okay, whichever the answer is, whichever you are comfortable with. Okay. Anyway, anyway, so how does it look like? So what's the answer? So the answer is still 2 sine omega t divided by omega. So you can see here, and for omega equal to 0, it is 2t. We just saw that for omega equal to 0, this is 2t. Okay, now you can see this is a sine term, okay, which would have had its magnitudes, constant over an envelope, but then the denominator goes on increasing. Denominator goes on increasing. So when denominator goes on increasing, this entire thing has to come down. Okay, entire thing has to come down, and you end up getting the bell-shaped curve. Okay, you end up getting the bell-shaped curve. So there you are. There you are. The Fourier transform. Okay. So here is the expression, and any complex part here? No, this is purely real thing. So at omega equal to 0, you substituted 2t. Then afterwards, this goes on decaying. Okay, gave you this thing. Okay. So this also one more standard result which you are supposed to remember with this t. Say wave going from minus t to plus t. You have this t. The next numerical. What will be the next numerical? Okay. So what about sinc? This is expected. A sink in the frequency domain gives you a rectangle in the a rectangle in the frequency gives you sink in the time domain. They usually do not do it the other way, okay? Because who wants to get the trouble of getting the Fourier transform for a sink? Okay, it's going to be very irritating. But we will use the formula templates instead. Okay, in this case. So what happened? X of j omega equal to 1 from minus omega to omega. Okay, 0 for omega greater than omega. That is the template. Okay, and we'll simply apply which formula. Now you can see x of omega was given. We are trying to arrive at x of t. Okay, so what we'll do, we'll apply the formula for inverse Fourier transform applied nicely. E to the power j omega minus omega 2j was also there, so we got it as sine. Okay, now that this is a standard form. Okay, sine of omega t divided by pi t. Okay, this is a term sync. Okay, I don't know how many of you will be comfortable with this term. I am comfortable with this formula only. I am comfortable with this particular formula only, or you can either go for this one. Anyway, this is a formula which I am comfortable for. Omega equal to t equal to 0. For t equal to 0, what is it? So sine omega t for very small t is simply going to be omega t only. Omega divided by pi t. So omega by pi for t equal to 0. And we have another ready set of results which we'll use later for the reference. Now let me just stop here and I will call you for the, I will send you the ID and password. Okay.